Welcome to the 9th video in the Standard Quiz Model series. Once again, we're going through the Standard Quiz Model itself for AP Calculus AB Term 1, focusing on each of the questions. This time we're going to focus on question number 9, the tangent line question. And truthfully, the tangent line question, even though it is, the heart of Calculus A, or the beginning of calculus, it's one of those pieces that I think comes out pretty easy, but there are lots of places to make a mistake, either with how you write your derivative or evaluating even the function itself. So we're going to jump right in. We're going to start with question 9a, which is the most basic question that could ever be asked. It's probably one that would only be asked during the first week. And what we're asking you to do is find the equation of the tangent line to 3x squared plus 5 at x equals 3. So although I wouldn't normally go through this much trouble, it's worth pointing out that 3x squared plus 5 is a positive parabola. It's been shifted up 5. We're looking at x equals 3, so we're expecting a tangent line with a positive slope over there. So just worth pointing out, that's all just kind of ways to kind of mentally check yourself as you go through and try to make sure you get everything correct. So to get a tangent line, there are a couple things you need to do. The first thing you need to do is figure out what the correct corresponding y value is. So specifically, if x equals 3, then y is going to be equal to 3 times 3 squared plus 5. Which in our case, we do want to simplify this for cleanliness. This is 3 times 9, which is 27, plus 5 is equal to 32. So that means our ordered pair of interest is the point 3, 32. So that's going to help us because our equation itself for any line is y minus y1 equals mx minus x1. We now know x1 is 3. We now know y1 is 32. What that leaves us with is to figure out what numeric value gives us the slope at x equals 3. So to get there, we do the second piece, which is to evaluate the derivative. So y prime in this case is going to be the derivative with respect to x of 3x squared plus 5. When you take this derivative, this is a very simple derivative. It's just using the scalar multiple property as well as the power rule. We end up getting 3 times 2x plus 0, which is equal to 6x. But keep in mind, 6x is not our slope in this case. 6x is just the derivative. So this is the formula through which we could find all of the slopes on this graph. We want specifically y prime of 3, which in our case is going to be 6 times 3, which is 18. So we now know the slope is going to be 18, which means our tangent line equation is y minus 32 equals 18x minus 3. So very straightforward, not to draw a box, but a very straightforward tangent line equation question. Just test whether or not you know the technique. Our second example here, start throwing in some tougher stuff here, some tougher derivative rules as well. We want to find the equation of the tangent line to tangent of x at x equals pi over 3. So we talked about it a few moments ago, what this would look like. So the first move we need to do is we need to consider what the y value is. So specifically, if x equals pi over 3, that means y is going to be the tangent of pi over 3. And again, if that's not a number that you know off the top of your head, you can quickly draw it in. Pi over 3 is 60 degrees. Means this is going to be a root 3, 1, 2. Tangent is going to then, therefore, be equal to square root of 3. So once again, keeping in mind what our tangent line formula itself looks like, we now know x1 is pi over 3. We know y1 is root 3. We're left needing to calculate the slope. So next, to find the slope, we're going to calculate y prime, which is the derivative with respect to x of tangent of x. The derivative of tangent of x can be found using the quotient rule, or you can just remember it and memorize it as secant squared of x. That is the same thing, I'll point out, as secant of x squared. Some people have trouble remembering that and realizing that. So that's what we need to plug our pi over 3 into. So y prime is going to end up being secant of pi over 3 squared. Now, we don't have to simplify, but in this case, it's not simplifying. We have to actually evaluate that function and make sure we can find the correct value. So I'll remind you, in little trig stuff, that secant of pi over 3 is the same thing as 1 over cosine of pi over 3. And of course, we're going to square it. Now, cosine of pi over 3, following that same pattern, we already drew what the pi over 3 triangle looks like. So if that's our pi over 3, the cosine is going to be adjacent over hypotenuse, which is 1/2. So that means our value is going to be 1 over 1/2 squared, which is going to be the same thing as 2 squared, which is 4. So our slope at this point is actually going to be 4. So our full tangent line is y minus the square root of 3 equals 4x minus pi over 3. And again, there is our tangent line equation. Again, not too crazy, but you do have to actually know tangent's derivative and be able to evaluate some basic trig functions. Okay, our third one. I feel like this is a pretty good representation of those straightforward tangent line equations that we asked during term 1. So you're asked to find the tangent line equation at x equals 5 for y equals 13 over x squared. So in digging in here, the first place I'm going to begin is once again figure out the y value. If x equals 5, y equals 13 over 5 squared, which is the fraction 13 over 25. So in a sense, we've got the y value already covered. It means that we're going to pass through the point 5, 13/25. Nice to know that, but of course the slope is the bigger challenge. So if we want the slope, we need to calculate the derivative with respect to x of 13 over x squared. But let me remind you that 13 over x squared is the same thing as 13 times x to the negative 2 power. The reason that's so helpful is this one just screams for scalar and power rule. So this is much easier to actually differentiate. In fact, this will be 13 times negative 2, x to the negative third, also known as negative 26 over x cubed. So that is our slope at any x value. Again, that's not the expression we're going to put in the tangent line because there's still an x in it. We want to find the actual slope at x equals 5. So in our case, if we want the slope at x equals 5, we're going to get negative 26 over 5 cubed, which we don't have to simplify, but is simple enough to simplify, as negative 26 over 125. So our tangent line here is y minus 13/25 equals negative 26 over 125 times quantity x minus 5. So there is our third example, tangent line. It's worth pointing out here that notice that we don't rewrite this in mx plus b form. We just leave it in point slope form for simplicity. We don't want to waste time doing that. We also don't want to potentially make a mistake and invalidate all that work just by doing a simple arithmetic mistake. So there are 3 simple examples, our straightforward examples. Let's look at our plus example. Once again, in this case, you might see some algebraic challenges. This one, though, involves a little bit more of a conceptual challenge. So in this case, it says that the tangent line to f of x at x equals 5 is 2x plus 7. Then it wants the tangent line to 3f of x at x equals 5. So there's a couple different layers that we have to actually work through here. So there's definitely some stuff to think about. So in looking at this one, the first place I'm going to begin is if y equals 2x plus 7 is tangent to f of x at x equals 5, there are 2 very important connections to make here. The first connection is about the derivative. F prime of 5 has to be equal to the slope of the tangent line. Otherwise, the line wouldn't be tangent. The slope has to match the curve's behavior in a sense. So f prime of 5 has to be the slope of this equation. And of course, the slope is equal to 2. So that tells me that f prime of 5 equals 2. So again, if you have a tangent line and you're told that it's tangent at a particular x value, you'll know the slope at that point instantly. The second thing is a little bit more subtle, but the second thing is that we can actually find f of 5 using the tangent line as well. Keep in mind, if you have some sort of curve and you know the equation of the tangent line at that point, the tangent line matches 2 things about the original function. Okay, that's a terrible line. It matches 2 things. First, it matches the slope, but second, it also has to match the x and y values at that point. Otherwise, it wouldn't intersect. In a sense, it intersects at that exact same value. So given that, we can actually find f of 5, or the y value of the original function, by plugging into our tangent line. So in this case, we're going to take that 2x plus 7 and plug in x equals 5, and we're going to get 17. So that tells us that the y value of f of x at x equals 5 is 17. So given this information, of course, we're not going to be able to construct anything brand new. We don't necessarily have to, though. What we do is we have enough information to determine some information about y equals 3 f of x. Specifically, if we want to know the y value, if we know that x equals 5, then we know that y is equal to 3 f of 5. And since we just found f of 5 as 17, we know y is 3 times 17, also known as 51. Second, if y equals 3 f of x, then y prime is going to be the derivative of 3 f of x. And if y prime is the derivative of 3f of x, that means that the derivative is 3f prime of x. And the reason that's so essential and helpful to us is that y prime at 5 is going to be 3f prime of 5. And since we found earlier that f prime of 5 is 2, we'll know that the slope of 3f of x is 3 times 2, which is 6. So we've now found our y value, our slope. We also obviously knew what our x value was, which means we can write our tangent line that we were interested in here. Y minus 51 equals 6, x minus 5. So in this case, yes, there's a little bit of algebraic work to do, a little bit of arithmetic work, but most importantly, you were just doing some conceptual thinking about what a tangent line tells us about a function and its derivatives. And we were able to solve the problem pretty cleanly from there. So with that said, that covers the 9th question. Again, I think it's one of the more straightforward ones, but again, lots of places to get caught. So there is question number 9 from the standard quiz model and term 1 of Calculus AB.